Hello, everybody. We have a problem here. It's so draw the DFA of a number that, when interpreted as a binary number, it's divisible by 3. So examples of those numbers would be 0, 3, 6, and 9. So in binary number, these are the representations of them. This is a video about the DFAs. So if you do not know binary numbers yet, then you can, search up a video on how to convert things into binary. It's quite simple. Okay, so for example, we have a number 6 divided by 3. So that gives us 2 remainder of 0. And another way to write remainders is to just get the result of the remainders to just mod it. So for example, in our case of 6 mod 3, our answer will be 0. So given a number k, the mods of the number would be 0 all the way to k minus 1. So in our question, 3, the mods for 3 would be 0, 1, and 2. So those are the remainders. If you divide a number by 3, you will get. And in binary numbers, if we have a current number, which is n, and then we append d to it, so if we append 0 or 1, our new number would be the base multiplied with the current number plus d. Okay? All right. So say we have a number which is 110, that is 6. And then you want to append 0 to it. So based on our formula, what would the number be? So the base is 2 times 6 plus 0. So it should be 12. And also, theoretically, it is 12. Okay? So the same way that we create numbers using this, we could also create mods using this. So the mods would be, so our new mod or remainder equals to the base times current remainder plus d. And then whatever answer we get, we'll just mod it with 3. Okay, so let's use this example, 6 and 12. So the remainder for 6 was already 0, and the base is 2 plus 0, which results in 0 mod 3, which still equals 0. Which still equals 0. Okay. So what does this tell us? So this tells us, instead of trying to figure out some sort of complex state machine that basically recognizes all these numbers all the way to whatever large binary you could ever possibly have, let's just simplify it and have a binary of remainders. So we'll just do the same thing for all the other mods, and we'll start drawing our diagram right now. Okay, so we know that it always accepts if the mod is 0, so that means it's divisible. So when the mod is 0, it's divisible with a number. So we'll have Q0 here, and then we'll accept it because okay, perfect. And so we want, what happens when you see a 1? So if we see a 1, our new mod would be 1. And let's get to the math. So if we see a 1, so the base is 2, the current remainder is 0, and then we append a 1. So each transition is like whatever we're appending to the digit. So that is the 0 plus 1, which is 1 mod 3, which still equals to 1. Okay, so this one takes us to Q1. So Q1 is a state whereby the remainder is 1. And then when we see a 0 here, we'll just self loop because it's accepting. So whenever we're at a base with that's accepting, and then we see we always add zeros, it'll always be accepting. It'll always be accepting. Okay. So that's done for that state. So now let's go to Q1. When we see a 1 in Q1, so we already have a current remainder of 1. So 2, 1, add 1. So that'll be 3 modded by 3, which equals 0. So if we see a 1 in Q1, we'll go back to Q0. Okay? But what happens if we see a 0 though? So that'll be 2, 1, plus 0. So that's 2 mod 3, which equals to 2. So we go to a new state, Q2. Perfect. So we already done all the cases for that. Now, we are in Q2. And Q2 is a state with a mod equals 2. So this is our Q1 calculations, and this is our Q2 calculation. So if we have 2 already, and then we see a 0, I'm sorry. So our current mod is 2, and we see a 0. So that's equals to 4. Yes. 4 mod 3. What does that result in? That results in 1. So it takes us back to Q1. But what happens if we see a 1? So 2, 2 plus 1, 5 mod 3. What does that result in? That results in 2 still. So mod is literally just a subtraction of the digits. So 5 minus 3, it's 2. So that will loop us back in Q2 if we see a 1. And there we have it. That will be our DFA that describes this language. So this shows that DFAs could go ahead and basically have systems that are much complex in theory, because we broke down finding divisibility by just using mods and having the amount of states that describe all mods. And here we had this theorem right here. And this theorem says that if, for example, we have 3 as our divisible number, the mods we'll have is from 0 all the way to k minus 1. So 0, 1, 2. So this shows that for a number k, to find divisibility using a DFA, we need k states. And here we have it. Here we have 3 states. So for divisibility by 3, we have 3 states. All right. Thank you for watching my video.